Welcome to the next lecture number 5, chapter number 7. And this topic is very important to understand that how Maxwell's fixed the Ampere's law. And as we know that the problem occurred during this equation number 4. In the previous lectures I have presented del dot del cross b, which is equal to mu naught del dot j. Not true for beyond magnetostatics. Magnetostatic means current is equal to constant. So for current is equal to constant, it should be noted that Ampere's law was purely theoretical. This point is clear that Ampere's law was purely theoretical. Then the Maxwell's also provided the theoretical arguments. Maxwell's used the equation of continuity. The equation of continuity, or the continuity equation, we know that the divergence of j, which is equal to minus partial divided by partial this. And if I find out rho, then I can find out this from the Gauss's law, just as this. So if I have to find out rho, then rho must be equal to epsilon naught and divergence of E. And this divergence, this value, I have to put in this equation, then partial divided by partial t, epsilon naught, and divergence of E. Further, this equation can be written in the form as minus divergence of this epsilon naught partial E divided by partial t. We can replace the derivative. So this is the equation del dot j that I have derived. If I write down the equation, this one, the del dot a cross b del, this is the del cross b, sorry. This is equal to mu naught del dot j. And I call this as equation number first. When this equation, the right side of this equation will be equal to 0. It is to understand this point, if the only reason is this may be equal to 0 if I subtract mu naught del dot j from this equation. Then At that situation, the left hand side and the right hand side may be equal. If we subtract, if we subtract uh, mu naught divergence of J from the right hand side of equation 1, this is the equation 1, such as mu naught del dot J minus mu naught del dot J. If I write down the right hand side in this form, then we can get 0, both sides. So this is actually, I'm going to proceed this problem to the correction term. This is a divergence. This is also very important. And I have to write down here this divergence J, which is equal to minus del dot epsilon naught partial E divided by partial T. And I want to erase this and del dot del cross B, which is equal to mu naught del dot J. This is the first term. And if I subtract del dot J from this, then now this will be equal to 0 and this will be equal to 0. Now it is clear that we can have this equation is correct. And now this is, I label this as equation 2. Further, let mu naught take this as a common minus del dot J. And from this equation, if you see this equation that we have derived this from the continuity equation del dot J, which is equal to this. If I put minus, if I take minus del dot J, which is equal to del dot epsilon naught partial E divided by partial T, then minus del dot J, this will be equal to this. So I can put the minus del dot J, the value of minus del dot J here, and this is equal to del dot epsilon naught partial E divided by partial T. Okay, and further, if I take the divergence and I write down like this, del dot, and this is mu naught J plus this is mu naught epsilon naught partial E divided by partial T, and this is equal to del dot cross B. Then if we ignore the divergence at both sides, it means that from this equation, if we remove the divergence from this side and this side, then we can get this is equal to this. And del cross B, which is equal to mu naught J plus mu naught epsilon naught partial E divided by partial T. And this is known as, if we remove this is the Ampere's law that previously calculated for the constant J. So del cross B is equal to mu naught J A plus this term, and this term is called Maxwell's correction term. This is called the Maxwell's correction term. Del cross B, which is equal to mu naught J plus mu naught epsilon naught partial E divided by partial T. And let's see, this is equation number 3. Now this is the corrected equation, and this corrected equation is also valid for magnetostatics. Magnetostatics means the current remains constant. It is also equal for J is constant, electric field is constant. If E is constant, then it means that this is a magnetostatic. And for a magnetostatic, this term will goes to 0 because partial E divided by partial T, this goes to 0, and we will have the previous Ampere's law del cross B, which is equal to mu naught J, that already calculated by Ampere's. So I want to write down some things because it is important. This corrected equation is also correct for magnetostatics, i.e. if E is constant, then partial E divided by partial T is equal to 0, and we get del cross B, which is equal to mu naught J. This is for the magnetostatics. At Maxwell time, it was hard to measure the correction term due to unavailability of the experimental setup, because this was done only theoretically and there was no availability of the experimental setup. So no one at that time checked this experimentally. So this point should be clear. But the confirmation of Maxwell theory has been done in the Hall's experiment in 1888. In this experiment, it was confirmed that light is an electromagnetic wave, and Maxwell term or it is also called correction term. Correction term was confirmed. As del cross B, this is the equation that Maxwell corrected, and mu naught epsilon naught partial E divided by partial T. From this equation, one can say that by changing the electric field with time, one can induce the magnetic field. Previously, from the Faraday's law, if the magnetic field is changing with time, one can induce the electric field. But from this equation, we can see that by changing the electric field with time, one can induce the magnetic field. Maxwell called the extra term JD, which is equal to epsilon r partial E divided by partial T. This extra term they called as the displacement current. Displacement current. But it should be noted, I emphasize that it should be noted that JD has nothing to do with current. It is not a current, but just they call this a displacement current. But actually, this is not a current. It should be noted this point. Further, let's discuss more about this equation. This is a theoretically that Maxwell's fixed this term and corrected this equation, but this was theoretically, as I have already discussed. But how one can understand that it is true experimentally. This paradox may be resolved like this. Consider we have a parallel plate capacitor and this has been connected with a battery and a current is flowing in this loop, and initially if we have this loop, if we consider a plate, a flat surface, then here the electric field is equal to 0 and I enclosed, which is equal to I. If we consider this loop, then the current passing through this, the electric field will be equal to 0 and the I enclosed, if I find out the I enclosed must be equal to I. And then one can get the Ampere's law, and we can get the Ampere's law. One can get the Ampere's law in integral form like this: B dot dl, which is equal to mu naught I current enclosed means I. Then that is true when I consider the loop, the flat surface like this. On the other hand, if I consider a balloon shaped surface, if this is not like this, but this is like a balloon, then what will happen? This is like a balloon and this is passing through this capacitor. Then at this surface, how we can calculate the current? And here From this loop, this balloon type loop, one cannot calculate the current passing through this. No current will pass through that surface. So it means that the I enclosed and this balloon type, because it is passing through the in between the capacitor, so there will be no current passing through this. And for this situation, for this situation, the electric field change with time. Here the electric field, we have some electric field here, and this electric field change with time. If I write down here the electric field changes with time, and one can one can get the contribution. And for this type of balloon shape, the enclosed surface will be equal to 0, and E field, the electric field between the plates, the electric field between the plates must be equal to sigma divided by epsilon naught. The electric field between the plates, we can have such like an equation. Sigma is the charge per unit area, then this electric field will be equal to 1 over epsilon naught charge per unit area. And if I change this, take the derivative of this, then we may have partial E divided by partial T, which is equal to 1 over epsilon naught, and partial Q divided by partial T. This is current. So we may say that partial E divided by partial T, which is equal to 1 over epsilon naught A, and this is current I. And finally, if I write down A partial E divided by partial T, I can have the form this. A partial E divided by partial T, I divided by I epsilon naught. As we know, the Ampere's law with correction term, this one, del cross B, which is equal to this. The integral form of the Ampere's law with correction term or Maxwell term we may write, and after applying some Stokes theorem, I can get the B dot dl, which is equal to mu naught. If I write down this, it may take enclosed current and also mu naught epsilon naught integral partial E divided by partial T dot dA. So actually this is the integral form. If we take the integral of this, and this, and after applying the Stokes theorem, we can get this, and del dot dA we can get I, and this remains the same. In this situation, the I enclosed is equal to 0. The I enclosed is equal to 0. Then B dot dl, which is equal to mu naught epsilon naught and partial E divided by partial T dot TA. If this integral is applied to the total area, so it may have d dot dl mu naught epsilon naught and uh, partial E divided by partial T, and area of the whole surface, this is A. Then partial E divided by partial TA, I already calculated this one. Then A partial E divided by partial T, which is equal to I divided by epsilon naught, putting the value of this in here. Then what will happen? Let's see. Now this B dot dl, which is equal to mu naught epsilon naught, and the value of this already I have calculated. Then I divided by epsilon naught, then this epsilon naught will cancel with this epsilon naught, and B dot dl, which is equal to mu naught I. This is been remain the same for the constant. For the magnetostatic, we already have B dot dl, which is equal to mu naught I. But for beyond the magnetostatics, I use the same equation this, and I found the same result, mu naught divided by I B dot dl, which is equal to mu naught I. So for both the cases, this equation is correct. Finally, Maxwell write the equation in compact form as 1 divergence of E, which is equal to rho divided by epsilon naught, divergence of B, which is equal to 0, and curl of E, which is equal to minus partial B divided by partial T, and curl of B, which is equal to mu naught J plus mu naught epsilon naught partial E divided by partial T. So these are the compact form.
These four equations and F is equal to Q into E plus V cross B, these five equations gives us the complete set of classical electrodynamics. At last, the four Maxwell equation we can write down in this form, such as del dot E, which is equal to rho divided by epsilon naught, divergence of B, which is equal to 0, and curl of E plus partial E divided by partial T, which is equal to 0, and curl of B minus mu naught epsilon naught partial E divided by partial T, which is equal to mu naught J. So this is the complete set, because the reason is the source and the electric and magnetic field are separated, because the source is rho and J at one side and the electric field and magnetic field is on the other side.